Okay, good. Hello, everybody. My name is Anton Stroganov, and I'm a product management at LIGENTEC. Unfortunately, Michael Geiselmann didn't manage to make it to the conference today, therefore I will be substituting him for this presentation. And the topic that we'd like to discuss today or to present to you is just a bit of a journey in terms of the integrated photonics. So it's entitled Low-Loss Photonic Integrated Circuits from Fast Prototyping to High Volumes. First of all, I will tell a couple of words about who we are, where we are, and what we are doing. So generally, our headquarters are based in Lausanne, next to EPFL, and generally our technology and the company originated from there. But overall, the company is European-based. So we have also offices in Paris and France. We have some people working from Belgium, Spain, and other places in Europe. Therefore, we are really distributed, really European and integrated team. And we're trying to maintain the leadership in the silicon nitride technology in Europe, in fabrication, and we have a global outreach. So, as I mentioned, we try to maintain the leading positions in our domain, and our customers generally come from all over the world, and they work in many different areas, starting from the conservative ones, such as communication, safety, sensing, metrology, and so on, to new ones, hot topics such as LiDAR, quantum technologies, space technologies, and so on. And generally, they cover the whole spectrum of possible customers. So they can be from disruptive startups to research institutions up to large technical corporations. But before we go further, main question, why do we need PICs at all? So I will try to provide just a single example, but I hope it will be representative. And generally, it should cover well the whole reasoning why all the industries go to integrated photonics. So this example is well known. It's generally about the frequency comps. And here on the slide, you can see an image of the first self-reference comp, which was basically demonstrated in 1998 in Max Planck Institute in Germany. It's a huge technological advancement of that time, but you can see that the system is very complex. It's bulky, it's a lot of discrete components, tens or hundreds of them, and it occupies up to several cubic meters of the space in total. About 10 years later, Menlo Systems, a company, commercializes much more compact solution, shoebox size, and much more user-friendly, and it's already a great progress, great technological advancement of that time. And now, about 15 years later, we see demonstrators of integrated frequency comps, which contain single chip or multiple chip assembly, which fit in a standard butterfly package. And here we're speaking already about cubic centimeters of the volume. And we see it as a huge progress when we go from this to this, fully integrating the system on chip without losing too much in terms of the performance. So let's just reiterate why we need integrated photonics. Well, the overall idea is simple. We would like to transfer bulky, expensive, complicated optical systems, which are not always easily scalable, on chip. So the obvious benefits are miniaturization. You decrease the size, weight, power, cost, and complexity. There are no discrete or moving components and parts, and it increases your reliability of the system. And one of the most important parts of the integrated photonics, it brings scalability. So you can reproduce your system as many times as you need with a high reproducibility of the performance. If you need millions of devices, you can do it. 10 millions, billions, you just go and do it. Are there any real-world examples? So you can imagine that with the majority of the customers with whom we work, it's very hard to name them because of all the confidentiality issues, but there was at least several examples where people went public announcing that they work with our technology. And here on this slide, you can see an example of a real quantum computer implemented using our technology. And generally, it's being run and it can be accessed through the cloud. So generally, it was demonstrated that you can make a photonic quantum computing using LIGENTEC PIC technologies. Here, just to give you a bit of an understanding where we see us in terms of the ecosystem position, what we do, what we don't do, and where we try to be. So generally, our main business and expertise is chip manufacturing. So we fabricate chips based on silicon nitride from low volume up to from low volume prototyping to real volume production. The IP is always staying with the customer, and we try to collaborate quite a lot within the ecosystem with, on one hand side, design and software houses, and on the other side with the packaging and assembly houses to ensure that there are well-established technical interfaces, so there is a smooth development or research process for any customer or partner of us. A bit more on the technical side, so I mentioned it already that we are providing the service of fabrication, and we are generally technology-based company. So what we do, we provide a mature and versatile platform with modular approach, and we have a unique expertise in thick film processing. Just to elaborate a bit on that, so what we do, we use silicon nitride, which holds generally the same benefits as any silicon photonics, especially speaking about the compatibility with the CMOS processes and equipment, but also it has some additional beneficial features. I will not go too much into details, but you can address generally much more applications due to wider transparency, higher power handling capability, higher thermal stability, and lower loss. But generally, how we distinguish ourselves from other people working with silicon nitride is our expertise with thick film. What means thick film? Here we're speaking about 500 nanometers and above. Generally, we typically work with 800 nanometers. And what it implies that generally your mode, even at C-band or even above, is very well confined inside the waveguide. So you don't feel the sidewall roughness, which is the main origin of the imperfections, and therefore you have much lower loss, you have lower phase errors, and what is important, you can have very tight band radius, which means that your system can be really compact and have really small footprint. Generally, how we approach it, we have a basic process of fabrication where we supply passive circuits with several different thicknesses of the nitride. So we standardly work with 800 nanometer, 150, 400, but generally we can address any other thickness. And then what we provide is additional add-on modules which add some functionality on top. So you can either form partially etched rip waveguides, you can have local cladding removal for integration with other materials or for sensing purposes, you can have integrated heaters for thermo-optical tuning of your system, or you can even have multi-layer photonic structures. And what is nice about these modules is that you can choose freely any of them, or you can combine all of them on a single PIC. So it's cross-compatibility of the modules. You have all the flexibility to fabricate what you really need. And of course, as any foundry, we have an extensive PDK of pre-developed components, which you can just drag and drop in your designs. Speaking of which, just several examples of the PDK components. So here, what is most widely demanded is generally all the splitters, and you can see that we have a variety of them implemented as directional couplers or as MMI, multi-mode interferometer couplers. And generally, we have a variety of splitting ratios or even configurations such as 3x3 or 4x4, which can be used as a 90-degree optical hybrid. So you have everything ready to be used. You don't need to invent anything yourself. And just here, you can see an example of the performance. So what it implies that generally these components are low loss, they are broadband. You can see that the response is very flat in the whole measured spectrum range. They work for both polarizations, so you can have this diversity, which can be important for a variety of the systems. And what is important, they are reproducible. We see an excellent reproducibility within wafer and wafer to wafer, run to run. So anything that you may need to scale up from prototyping to real volume production. Another example, which can be quite widely used in a variety of the systems, is delay lines. So generally just a long waveguide which can be used as a part of an interferometric system or for any other purpose on a chip. And generally with high confinement you can have them, first of all, very compact, and therefore it implies that on a chip you can have very large delays. So speaking about large delays, what we mean is that you can have a waveguide up to a meter or even more if you need on a small chip, which is just several millimeters by several millimeters. And of course, in this case, it's not only about the size, it's also about accumulated effect of the loss. So here we're speaking about the low loss in our platform of 0.1 dB per centimeter for single mode waveguides, but generally you can do some tricks to go even beyond that. And we have, for the moment, standardly shown that some of the wider waveguides can show up to 5 dB per meter propagation loss. And generally, what can be important for communication and other purposes, the waveguides can be symmetric or asymmetric, and therefore you can control the polarization. It can be polarization maintaining, or it can be polarization insensitive propagation. Next, just several examples of the use cases, how people use our platform. I believe it can be relevant here. Arrayed waveguide grating, so basically multiplex and demultiplexing systems. This slide is just to showcase that we implemented it in a variety of different wavelength ranges, O-band, C-band, near infrared, and even visible. And generally, all of them, they show low loss, both insertion and propagation, low phase errors, and therefore good performance, low crosstalk, and low temperature dependence, which is important. And it allows it to be much more suitable platform for AWGs than, for example, SOI platform or 3.5 material platforms. Another example, which is quite a hot topic nowadays, it's narrow linewidth lasers, which can be tunable, and it can be tuned in a quite wide range of frequencies. So the idea is quite simple, that you take your passive cavity in silicon nitride, you take a simple laser diode in a gain chip, you combine them, and from very simple chips, you can get very performant laser. So with a simple laser diode, which you can purchase anywhere, when you combine it with a silicon nitride, you can obtain quite impressive characteristics. So the line widths can go down to the kilohertz range with a side mode suppression ratio of 70 dBs. Powers, it can be several tens of milliwatts, or if you combine more gain chips, it can go up to more than 100 of milliwatts. And the tuning, in this particular implementation, it was around 60 nanometers, but there are state-of-the-art devices which can tune up to 200 nanometers. So I would say that if you take simple commercial devices and combine them, it provides you quite a good performance overall. Next part, fab in volume. So it's not a problem anymore, and we announced it publicly last year that we transferred our proprietary developed process to the large commercial CMOS foundry. So now we transferred it to X-FAB in France, and we anticipate that together we create the largest capacity foundry service for integrated photonic circuits in Europe. And on this slide, I just like to guide you through the things where we believe we can provide real added value. So we see generally our mission in assisting you in transferring your innovative photonic integrated circuits ideas on their way to the market. So here we have 3 pillars or stages. The first one is offer low barrier entry points. So basically here we're speaking about standardized runs and open access to the technology for fast prototyping and for research purposes. And this is generally based on our well-established AN technology with fixed layer stacks, extensive PDK, and so on. So basically all the things that we've discussed on the previous slides. And you can access this technology via standard MPW runs, multi-project wafers runs, or custom runs if you need them. Next part is development and optimization. So wherever what is shown in the first pillar is not sufficient, we do offer custom layer stacks or custom process integration and development, which requires a high flexibility and process integration competence. And I believe we are one of the not so many players who can really offer such kind of services in Europe. And the last part is the third pillar, basically the product supply, because we see that there are quite several areas where the quality and the supply guarantee are key. And there are peak applications where, for example, one peak goes into a larger system, which is quite expensive. It can be several tens of thousands of euros per unit. And therefore, such kind of applications are typically not of interest for standard classical foundries. And we try to fill this gap by enabling this and offer pilot and niche quantities as well as larger volumes with the same quality and commitment. For that, generally we offer MPW runs, as was mentioned before. We have quite a lot of them. They have very nice schedule. We have 5 runs per year at least, with a variety of different thicknesses. We offer full support with a training, post-review session, and all the DRCs included. And probably, as my time is coming to the end, I'd like just to summarize what we've seen on the previous slide. So first of all, integrated photonics gets more and more widely used. We see a lot of attention and progress from many different industries, and we see how it's conquering new domains. It brings size, weight, power, and cost reduction, makes system easily scalable and highly reproducible. And LIGENTEC is a technology and service provider for the domain, giving you access to the mature technology with high confinement of the optical mode, low loss, small footprint of the system, and high power handling capacity. You have full creativity with a modular approach and pre-developed library of the components, and you can access our technology within MPW, dedicated runs, or engineering projects where we co-develop the product according to your specifications and the needs. Thanks a lot for your attention. I'll be glad to address your questions either here, or you're welcome to come to our booth number 330, which is just behind you here. Thanks.
Thank you. Thank you. One quick question regarding your PDK here. So do you incorporate the different materials, for example, like polymer, like other materials? How they work that way?
Yeah, so it's a good question. So generally, as I mentioned, our main business and expertise is in silicon nitride, and we continue to keep it this way. But we, of course, recognize that passive platform is nice, but you always would like to go active. That's why we try to work on co-integration of different materials. So we have activities related to lithium niobate, for example, for fast modulation, or integration with 3.5 materials for photodiodes or for gain materials. So it's ongoing work. We have R&D runs and R&D projects related to that, but we do not offer it as a standard offering yet.
Okay. So any other question from the audience?